Welcome to another RDWorks Learning Lab. Today we're not going to be using the China Blue machine, we're going to be using the light blade machine for a very specific reason, and it's all to do with the lenses. Over the past few months, and I've actually forgotten how long it is now, I started my quest on trying to understand how to get decent engraved pictures out of these machines. And it all came back to one very simple aspect: small dots. The smaller the dot, the better the picture quality. And one of the problems that we've had and have been chasing all this time is how do we get the machine set up and how can we use the lenses to get the smallest possible dot. The smallest practical size dot that we seem to be able to get is around about 0.2 of a millimetre, and that limits us to a resolution of about 127 dots per inch, or PPI from the picture point of view, which is not a very high resolution. Now, there are companies around, and I mention Thunder Laser in particular because I've got a great respect for that particular company. They're a quality Chinese company. Okay, their machines are not as cheap as these eBay machines, but you know, they provide a good quality product and an excellent backup service. And as I said, I've always had a great respect for them as a company. I know that in their product range, they sell a standard nozzle assembly, this sort of nozzle assembly, with something that looks very much like this, which they call a standard nozzle. And I've got no idea what the lens is inside. Because it's this design of assembly, I'm pretty confident that what they've got is the same as these, which is a lens which is buried up inside here. Now this happens to be a 2.5 inch lens, which is why it's sitting back here. This one is a 2 inch lens, which is why it's sitting closer to the front. But you can't get a 1.5 inch lens in here and get the focal distance here, because this length is just too long. And so consequently, with this assembly, if I want to use a 1.5 inch lens, I've had to modify this assembly myself to make it suitable for taking the 1.5 inch lens inside the nozzle here itself. This is the seating for the 1.5 inch lens. Now, on my China Blue machine, I have a 1.5 inch lens, 2 inch lens, 2.5 inch lens. It doesn't matter what size lens I use because the lens is mounted with a screw thread in here. No matter what focal length the lens is, it always sits just here. Now, that's both an advantage if you're using a short focal length lens and a disadvantage if you're using a 4 inch lens, because a 4 inch lens has got a wide beam to start with, and it would probably be down here somewhere, the distance to the work from the nozzle. And because of that, what we have in the end here is a very large hole, so that the beam on a 4 inch lens maybe doesn't hit the side of the nozzle. So you get this big hole with this style of lens fitting. When we use this style of lens fitting, we have a very small hole in the end of the nozzle, which is absolutely great for control of airflow, because the focal point is always approximately the same distance below the end of the nozzle. We only need a very small hole in the end of that nozzle because by the time the beam gets down to here, where my thumbnail is, it's already a very small beam passing through that nozzle. So we only need the small hole, which means we get a good controlled jet of air from our air assist. And it's a very short distance away from the work. So we get very good cutting properties from this style of nozzle. Coming back to where we were a few minutes ago talking about the Thunder Laser assemblies, I've got to assume from external viewing only, because I've got no actual knowledge of the system, that because their standard nozzle looks exactly like this, that the best that they can have in there is a 2 inch meniscus lens. Now, a meniscus lens is different than the standard plano convex lenses that I've got in here. Now here is a plano convex lens, and this is what a meniscus lens looks like. It's got a concave bottom to it. Now the problem is with any lens there is a problem, particularly with the plano convex lens, and that is that the larger the diameter of the beam, the further out you get from the centre of the lens, the beam travels inwards at a different angle to what it does when it comes through the centre. And so if you look carefully here, you will see that there is a great amount of uncertainty, let's call it that, about where the neck, the spot size for the beam actually is. So with a plano convex lens, you are never going to be able to get a really crisp, sharp focus point. With a meniscus lens, because this lower curved surface has an effect on the light beam as it exits the lens, it helps to correct this uncertainty that we have here. These beams from the outside cross over there, and the beams coming down the centre cross over here. So they're still not perfection, but it's a lot better than the plano convex lens. The first thing I'm saying is I believe that probably Thunder Laser are using these better quality lenses to get a really nice, crisp, sharp point. And it's probably a 2-inch, because you can't physically get a 1.5-inch lens into that assembly unless you do something special to it, such as I've done. Okay, so here's our two lens types. Most of what I've been working with have been this type of lens. So I'm already on a bit of a loser to start with, because I've got this uncertainty at the focus point. Now let's take a look at the beam, a picture that we've been very familiar with, because I keep telling you that the energy density across this beam is not flat. It's got a much higher density profile in the middle. There's more power in the middle of the beam than there is on the outside of the beam. But when we focus the beam down, we still have got that same energy profile. So although we've got this high energy density within this very small spot, which gives us the potential for producing an even smaller spot if we can just kiss the end of that beam, the high energy end of that beam, we shall get a very small spot, which is smaller than the theoretical spot size. Look at this, a lot smaller than this theoretical spot size here. But in reality, if we put a spot down, we're burning with this end, and because the energy density is disappearing out towards the edge and getting lower and lower, it isn't able to do as much damage. So what will happen is, around the outside of this little high energy spot, we shall get a lower energy area, and that lower energy area is not doing as much damage. And with an organic material, not as much damage means it won't punch a hole through, it will actually only scorch around the outside of the hole. We shall get a brown halo around a very small, microscopically small hole. And it's the brown halo that is effectively the dot that we will see when we produce a picture. And that halo comes out to, typically, in practical terms, 0.2. That means we're automatically limited to 127 pixels per inch with a 0.2 diameter halo. There's a classic example with wood. Burning and scorching and producing this brown horrible debris around the outside as the resin gets blown back down onto the job, the smoke gets blown back down onto the job. Acrylic does not scorch, it evaporates. There we go, there's some silly experiments that I've been playing with. Now if I catch this in the light right, you might be able to see around the edge of these holes here just a little bit of a change of texture. There's no colour change, it's just a little teeny weeny bit of maybe melting or softening of the material. Off of this mirror polished finish on here, you can just see a little bit of surface distortion when I catch it in the light right. So that's all that's going to happen to acrylic. We don't scorch it. And if we don't scorch it, hey, look, we might have the possibility of getting small dots in acrylic because we don't have to scorch it. So that's a fascinating possibility. Here's another material which we have already experimented with and dealt with. This is anodized aluminium. This is another material that doesn't burn, it doesn't scorch. This is a dye that's penetrated into the surface, and the white here is the aluminium oxide that has been produced on top of the pure aluminium. Now the dye evaporates out of this surface at something like maybe 200 or 300 degrees C, whereas it's probably 1500 degrees C to melt through this white surface that's underneath. So provided we tune our power such that it produces more than 300 degrees C and less than 1000 or less than 1500 degrees C, we can keep going over the same spot again and again and again, and we don't produce any colour change other than we remove the dye and we get to the white background. So this is a fantastic material to work with, where we're looking to possibly get high quality images because we don't get scorching. And then we've got to look at glass. Now glass works in a completely different way, and we shall have to deal with that as a separate subject because it doesn't actually work with a burning process. The secret to getting a small dot will be, first of all, to try and use a meniscus lens. And the second thing is to try and find a way to make the dot even smaller. Now, as I said to you, if we look closely here, even with this meniscus lens, we've got this uncertainty. And I'm using this picture because this is a larger, more easy to see picture. If we can reduce the beam size and just use this part of the lens, then all of a sudden we get a completely different set of conditions. We don't get this large D here, we get a very, very small, well-focused area. So there is potential for producing a smaller focus point if we can use the central part of the lens only. We don't get this effect here, which is something called spherical aberration. Now I'm explaining all this to you because it is an important part of the principle of what I'm just about to show you. I have been fiddling with these lens systems over the past couple of 3 months, on and off, just a few minutes here and a few minutes there, and failing, to be honest. But I have, I think, come to a conclusion where I think I can succeed now. So what we're going to do today is to go on a journey of discovery using a piece of new kit that I have manufactured. When I explain what I've done, you will see why I can't use this lens system here. Now, as part of this lens system, you'll notice that there is a thread in the back of the lens tube as well as the front of the lens tube. This lens tube was supplied with this machine to take and it was supplied with a 4-inch focal length lens in it. Okay, so I've now installed the 4-inch focal length lens into the back of this assembly. This is the lens assembly that I would normally strip this out of, and I use my 1.5-inch special lens assembly in the front here. Let me just install this back into the machine and I'll show you what we've got. I've got the 4-inch lens at the top here, and so the beam will actually come down and it will focus probably somewhere down around about here. But the question is, what size beam is it as it passes this point here? Well, let's put a piece of masking tape on here and we'll just press the pulse button. And the answer is around about 2 millimeters. So by the time that 4-inch lens gets down to here, we've got a 2 millimeter diameter beam. And what did I say we were looking for? We're looking for a very small beam down the center here to get us a very small point. So if we've got a 2 millimeter beam at this point here, why don't I put another lens in just here, like a 1.5-inch lens, and that automatically means that I'm putting a very small diameter beam into a lens which will focus it down to a much smaller and more accurate focus point. That's the principle that I'm working on, and I'm assuming that that's a similar principle to that that's being used by Thunder Laser. If you put 0.1 dots together without them overlapping, you're going to finish up with 254 per inch. So if we have a dot that's half the size, we're going to finish up with 508 per inch. This is the path that we're going down. We're in the quest for the smallest dot that we can possibly find, and the only way that we're going to be able to do that is to make the beam smaller, and then maybe we can use just the tip of the beam. So it's not a 0.05, maybe it's a 0.01 dot size, 10 microns. Who knows what we can get to. What I've done is to manufacture this. It's an engineering plastic called Delrin, is the trade name, but it's an acetyl copolymer. It's a very stable engineering plastic. It's got quite a high melting point, but trust me, it will melt and it will burn. But hopefully if we get this set up right, we won't get any heat back from the front because we're only engraving, and we won't get any heat from here because we're not going to let the beam touch the plastic. So we should be fairly safe. And this is a very cheap and easy way for me to make a lens holder. Maybe if I was manufacturing these in quantity, I'd make them out of anodised aluminium, like the rest of this job. So what we've done here, as you can see, we've got a 2.5mm hole in the middle, which is exactly the same size hole as we've got in that nozzle anyway. And what we're going to do is we're going to take a 1.5-inch lens and we pop it into the seat there. Now this is an 18mm diameter lens, whereas the rest of the lens assemblies in here are 20mm. But 18mm is perfectly okay for down here, and it's what I use on the other machine. So I have lenses that I can drop in and out of here and experiment with lenses. Now I haven't at the moment, although I have some on order, I do not have a 1.5-inch meniscus lens. What I have got here at the moment is a 1.5-inch plano convex lens, which we'll start off with. So we've already got a little bit of a problem in that we've got more uncertainty with this lens than we would have with a meniscus lens. But again, I have got some meniscus lenses of this size for the other machine, but they start off at 2-inch and 2.5-inch. So here I've got my lens, which is just dropped into that little seat there, and it sits just above the surface of this shoulder around the outside. Now what I've cut is a thin plastic washer. It's a shim which sits in there and sits on top of the lens, and now I've made that a press fit on there. It is not a screw fit. Now instead of this big bulky fitting that obviously I can't easily get into here, what I've done this time is I've got a piece of 4mm polyurethane, and I could equally well have used something a little bit more flexible like this piece of silicon, 4mm silicon tube. I'm using this piece of 4mm polyurethane tube, and I've drilled a hole through there which this slides into, and it allows me then to just push this up inside the 4mm air assist tube. That allows me to make a nice neat air assist connection into the nozzle there to protect the lens. Now over the buzz of the machine, I don't know whether you can hear this, but if you listen carefully, I'll just put my finger on there and build the pressure up. There is a very, very small amount of air that's flowing through here, even though the machine and the air assist is off at this moment in time. That's the natural protection that's there for the lens at all times, even with my air assist off. Okay, as I mentioned to you a few minutes ago, acrylic offers us the greatest amount of promise because it doesn't burn a halo around the outside of the high energy spot that we're going to make in the surface there. So we're going to use this as our first piece of test material to see what we can achieve. What size dot can we achieve? Now I'm going to use my little standard 256 dots per inch test pattern, where the bottom row of dots in this test pattern are 1 pixel, 1 pixel space, 1 pixel, 1 pixel space. So every pixel is 0.1 of a millimetre, and that allows me to use the dot spacing to assess what size the dot actually is that we're producing. Okay, now the focal distance for this lens that I've got in here is nominally 1.5 inches. I have already established that the gap under here has got to be 6 millimeters to get the best focus. So the lens is about here in the assembly, and that probably means that the focal distance for that lens now has changed from 1.5 inches to something like 3/4 of an inch. Now that's quite staggering, isn't it? The fact that, you know, just the central part of that lens is working at a focal distance of around about half what the nominal focal distance for the lens is. So that just shows you the amount of spherical aberration that's taking place. Okay, so I've got no idea what power and speed I should be using on here, but generally I think I'm going to be working right down at the bottom end of this machine's capability. Now the tube on this machine will fire probably at around about 9%. I'm going to start working at around about 12%, and we'll see what sort of dots we produce with my test pattern. Bear in mind that the power that you put into a dot is dependent upon the power and the amount of time that you allow that power to sit in one spot. So I've got a speed of 150 millimeters a second that I'm going to run this test at. If the dots aren't there, I could slow the speed down and make the power last in the spot a little bit longer to get a deeper dot. So this is a bit of a balancing act between speed and power. I'm starting off at 12% power and 150 millimeters a second as a guess starting point. Now I've got my little spyglass here, which allows me to fairly accurately assess what's going on with this pattern. We've already got far better dots than I've ever seen before. Those dots are not touching, but they are, I would say, just about 0.2 diameter. It means the power per dot is still too great. Okay, so we'll now go up to 200 millimeters a second and see what we get. We're getting there. We're gradually getting the dots smaller. Now those are smaller dots than I've ever seen before. The speed, let's push the speed up to 250. Now the great thing about changing the speed is that it means that we can very accurately control the power that we're putting into the dot. The power is remaining the same because it's 12%. If we go from 100 to 200, we're going to halve the amount of power that we're putting into each dot, because that relationship is directly related to the amount of time that the dot can be in one spot. Well, we're still doing okay. We haven't changed it very much, 250. So we got to 300. Now the problem that we're starting to run into now is the response time of the actual high voltage transformer as well. Can the high voltage transformer keep up with the pulse speed that we want? Because there are physics involved here, there are electronics involved here. It just isn't our imagination. We can't just ask for it to happen. So there's going to come a point in time when this high voltage power supply will just not be able to keep up with the request speed that we're after. And I think we may be getting towards that limit now at 300 millimeters a second. Well, I think we've done it. We've got to the 0.1. Yeah, we've got to 0.1 dots on the bottom line, but the middle row, yeah, we are only just about making it now. Can I add a little bit more power at 300 millimeters? Just a little bit more power, and get the dots back without making them bigger? That's the interesting question. So 350 millimeters a second and 14% power. Got to be careful because, as I said, you get a little bit of distortion around the outside of the dots. I think the dots are probably down at 0.1. Okay, so now I've got a 2-inch meniscus lens, which I'm going to pop into here instead of the 1.5-inch plano convex. Now, because it's a meniscus lens, it'll have a sharper point, but because it's supposedly a longer focus length, it may well have a bigger spot size. Personally, I think that it's going to be better than the 1.5 lens that we've got in there at the moment. And that's the 2-inch meniscus lens, sitting on there beautifully. That was not difficult to change, that was it? Now, I've got no idea what the focus is going to be like for this, so we'll have to very quickly do some tests to find out roughly what the focus is. But when I look at the holes that are going through these samples, I would say that the smallest hole, somewhere around about 8mm. We'll go back and test it on acrylic, because acrylic gives us the cleanest results. And this is 300 at 14%. Now, they are nice dots. Not completely there. Let's back the speed off a little bit. So still a little bit on the fast side. Not every single dot is coming out. So that's 200, 250, 14%. Let's go back to 200, 14%. Well, we've got a full set of dots, but they're down around about 0.15. Let's take the power down again to 12%. Wow, I would say they're just on the cusp of being 0.1. We've got that little bit of, as I said, melt distortion around the edge, which gives a little bit of a strange impression. Normally we'd examine them from this side, which is the side that we're burning them from. But in reality, when you're working with acrylic, you actually engrave on the back of the job and you look at them from the front, because that's where you pick up the light. And so consequently, when we look at it from the front, they look a fairly nice, neat row of dots at around about 0.1. And what we're seeing is the burn in the middle, about 0.1. Now, this is probably about as good as we're going to get. And this is with acrylic, which doesn't scorch, remember. So that's why I'm sort of slightly asking the question about the claims that Thunder Laser are making with their 1,000 dots per inch. So here's what we've established now with a 4-inch down to 2-inch meniscus compound lens. For acrylic, we've managed to get a 0.1 dot at 200mm a second and 12% power. Now, that's 12% power common mode. Let's do a couple of experiments with special mode to see whether we can get any better than this. Now, we're not going to finish up with 12%. We're going to probably start off at something like 25% with special mode, because the power is probably 50% less, but it's broken up into little teeny weeny power spikes. And I've got the user tab selected, and I'm going to read what's in my machine already, and we shall move down to, we'll find here scan mode, and at the moment it's set to common mode. So if I click on here, it gives me the opportunity to choose special mode. So now it says special mode, but I need to write that back into the machine, which it's now done. And so the machine is now set up in this special mode, and let me just check something else. Special mode, and I've got the Facula, which is the mark space ratio, basically set to 50%. So that means the power is going to be on 50% of the time and off for 50% of the time. So that's why I said I'm going to be setting this to 25%, roughly double that, to get equivalent of what we've just done. Now, they're nice dots at about probably 0.18, I would say at the moment, but they're all there. We can come down on the power a little bit. Let's go down to 20% and see what happens. Well, I would say we've got our 0.1 dots back now, and they're pretty good. There's a complete set of dots along there. They're very nice dots. So I may well start using that as my optimum speed. 20% special mode. Now, I've got some material here which is too big for the machine, so I'm just going to cheat a little bit and just chuck it in the machine like this. I'm even going to use that lens, and I'm not even going to set it. I've set the speed to, I think it's 110 millimeters a second. 2mm acrylic, 110 millimeters a second, and maximum power. Well, it hasn't quite cut it, but it's done the job. We've got another piece here which is 3mm. Let's do the same with that, shall we? We're going to start off with this extruded acrylic. Now I'm going to use light burn because I just love the graphics package in here, and it's got so much more flexibility than RDWorks. So the size is about right. I think we'll take that up to 150 is what we did before. Standard size 150 wide. Something else that we must do with this picture, first of all, because we're going to be doing this on acrylic, well, the background has got to be black. So what we've got to do is make it a negative rather than a positive image. And also, when the image is finished, we're going to look at it from the front, not the back. So therefore, we're going to have to reverse this image like that. Set the parameters. Now we've already decided here that the speed is going to be 200 and our power is going to be 20%. We are going to have air assist on, I think. We are going to bidirectional print. We're going to have a negative image. Right, we're going to set the dots per inch to 254, which gives us a 0.1 dot, which is what we calculated. But by setting the dots per inch to 254, it automatically sets the pitch for us to 0.1. Now all we've got to do is choose one of these many options down here for a dithering. And the one I'm going to choose to start with for dots is Jarvis. And we'll give that a try and see what we finish up with. From your perspective it might look okay, but standing here in front of it, it's pretty weak. That was a piece of extruded acrylic, but what I've got here now is a piece of cast acrylic. Well, let's just dust this one off. I think this is even worse. That was the extruded acrylic, and this was the cast acrylic. Not very good really, either of them, are they? Now, I could push the speed down, I could push the power up, I could do all sorts of things with it and improve that picture, but that's not what we're all about. We're trying to work to a formula that works. We're not trying to guess. So we're now going to select another option. And this time we're going to move on to something called newsprint. Now we've seen newsprint before, and at low resolutions we did it at 127 dots per inch, and it looked, if I say basic, looked at from about 20 feet it probably would have been okay, but close up it was terrible. We're going to leave exactly the same settings that we had before, and we're just changing to newsprint. Now this is exactly the same settings, just a different dither pattern. And if we zoom in and take a look at his nose, you can just begin to see some of the dots. Look at the eyes, you can see the dots on the eyes. Now this is at the 254 limit of what we should be able to do with a single dot. A 0.1 dot. Now what I'm now going to do is to double the resolution. We're going to go up to 508. Okay, now we're not producing much burning there, so all we have to do is to dust this down. just take the dust out of it. And that's what 508 pixels looks like. And I think you have to say that that's pretty staggering. I can hardly see any pixels on his nose. Look at the pixels in his eyes. Hardly there at all. I'm going to do something really stupid now, and I'm going to push this up to 1,000 pixels per inch. Now, we're not going to actually produce 1,000 pixels per inch, but what we are going to do is probably overburn quite a lot of them. So we have to bear in mind that our original test pattern was done at 254 dots per inch. Now look, I made a mistake on that pattern. Instead of 1,000 pixels per inch, I said 100 pixels per inch. And look what the result was starting to be. Well, we got to 1,000 dpi, but it didn't really do us a great deal of good. The 500 was substantially better. Well, let's see what the test runs like on wood, shall we? This is the 200 at 20% special mode. Say they're about 0.2 dots, so therefore I don't think I should be able to use much more than 254, double what the normal resolution is. Now I'm using newsprint again, and I've gone 4 times the resolution that I should be going. We're going at 508. I've got a 0.2 dot on wood, even though I've got my super fine lens in. I can't get a dot any smaller than 0.2. Now here we have a classic example of the problem you're going to get when you start messing around with wood. There's not a great deal of grain in this particular piece of wood, but look at the colour that it's engraving. It's hardly changing away from the parent material, and yet look what the same settings do here on this wood. In the same way that all cats aren't the same, all woods aren't the same either. I mean, these are all 4mm ply. They're all done with exactly the same power settings and exactly the same speed. Everything about these is the same except the wood. On here you'll see that I've got the grain direction showing. And the reason I'm saying that is because this one and this one are exactly the same material. This one was done with the grain this way, and this one was done with the grain that way. Now, the reason I'm pointing this out to you is because there are no such things as the right setting for any particular wood. I mean, this one looks quite nice and soft, but this one looks nice and crisp and clean. I mean, the best thing to do is to take a look at the whiskers, and you can see with the grain going this way, the whiskers have come out really nice and clean. They're not as clean on this one. They don't appear to be there at all on that one. They're just about there on that rather yellowy jaundiced looking one. And this one, although it might look quite a nice soft picture, the whiskers are not there at all. So by far and away the clearest picture is this one here. As I said, these are all done with newsprint. Now we assumed that we had a dot size of around about 0.1, 0.12. So technically these could have been run at 254 pixels per inch or dots per inch. In fact, these are all run at 508 dots per inch, twice the resolution. Now, with these dark parts here in the corner of the eye, there is not so much on that one. There's definitely 3D-ness on that one, which means that it is showing the signs of overburning on pixels. This one, just a little bit on the eye there. This one, nowhere else except on the eye. That the same, only just on the eye. And that one feels really nice except just on those black parts around the eye. But I mean, you won't notice that unless you're feeling them. So we've seen two extremes today, wood and acrylic. Acrylic is obviously a lot more stable material, but even so, we've got two types of acrylic which produce slightly different results. Well, the press fit nozzle that I made to go on here works for the one that I manufactured it for, but there are slight variations in this diameter here of this knurl. And when I came to fit my nozzle on different ones of these, it wasn't a press fit. It wasn't a good press fit, it was just a bit of a loose fit but still stayed on. While these have been working away on here, I've been beside on my lathe and I've manufactured an alternative nozzle with an O-ring in here. You press it on with an O-ring compression and it sits on there really nice and snug. So I will put a drawing of that, I will make a drawing of that available if you guys want it. A slight word of warning, this is the 2.5 inch meniscus lens that I had in when I was doing some more earlier tests, and after a couple of 3 hours worth of work I noticed that there is a little white spot in the centre there. Now I don't know if I catch it in the light right whether you can see that, but when I looked at it closely I think that what I've got is so much energy density there that I'm actually burning the protective coating off that lens. Just a word of warning, that's all, if you want to experiment with this. We've done all these cats here with this lens, which is a 1.5 inch lens. So let's have a look at the lens and see whether or not we've done any damage to this lens. As I catch that in the light, the answer is no. So I think it's all to do with the quality of the coating on that particular lens. This is a better quality lens, this particular one, and I've done no damage at all on there that I can see. And I must have run 2 or 3 hours with these at around about 45%. Well, yeah, it's been 45% in special mode. So that lens has really been working quite hard. Now, as you guys know, I'm a bit of a skeptic. I don't believe anything that anybody tells me. I have to prove it for myself. I have not been able to get dots smaller than 0.1 on any material. The best that I've been able to get is 0.1, really get 0.1 on a nice stable material like acrylic. I've not really been able to achieve 0.1 on wood, and I've certainly not been able to achieve it on anything like paper or glass. So if you happen to own a Thunder Laser high resolution lens, can I ask you to send me a personal message and I will send you my little dot pattern and you can see just how good your lens is at producing a 0.025. That's half the thickness of a hair dot on any material. I would love to see your results, please, because I'm very skeptical that anybody can get dots that small. On that gloomy note, can I say thanks for your time? I'll catch up with you in the next session.